Insert in binary tree. How do you insert a new node into a binary tree? The simplest answer for this is you insert in the first available position. How do you find the first available position? If this is your binary tree, what is a binary tree? Each node will have either 0, 1 or 2 children. No, none of the nodes will have more than 2 children. That is the speciality of a binary tree. If this is your binary tree, where would you insert? The idea is very simple. Do a level order traversal. That is, you go to the first level, then the second level, third level, fourth level. And in each level, you will be going from left to right. And while you are doing this, whichever is the first position that is empty, you will insert the. This is the logic to be used for insertion. So in this tree, which is the first available position, this level is completely filled. This level is also completely filled. This level is again completely filled. And what about this level? It is not completely filled. So you come from left to right and see which is the first available position. First position is this, which is not available because it is already filled. What about the second position? Yes, the second position is available because this node does not have a right child. So you can add a right child here. So you will do a level order traversal. For that you will have a queue. And what will you do? You will initially insert root into this queue. Then you will dequeue this root. And whatever are the children of the root, you will enqueue them in order. So you complete this procedure as you did in the previous level order lecture. But at whichever point you see that any particular node doesn't have both the left and right child, then whichever is the child that is not present, in that position you will insert the new node and you will stop the procedure there. This is the whole logic you have to use for inserting. So what we'll do, let us just see this with a pseudo code, so it will be easy to understand. And in this queue itself, it is easy to understand. I think I'll simply show with a small tree, so it will be easier for you. Maybe this is 10, 9, 8. These are the values, okay? This is the tree. So maybe these values are 11, 12, 13. So what will you do? You'll initially put 10 into the queue. So 10 is in the queue. This is the root. So you will dequeue the root. This is the procedure of level order traversal that we discussed in the previous video. 10 is dequeued. You will see what are the left and right child of 10. Left is 9, right is 8. So you will enqueue 9, you will enqueue 8. Then you will remove 10. So here it is not traversal. It is it is a attempt for insertion. So you don't have to note this node anywhere because you don't have to keep track of all the tracked nodes, all the visited nodes. Next, you will take 9 out of the queue. You will see what are the left and right children of 9. So left child is 11. So you will insert 11 into the queue. Right child is not present, which means you already found the position for insertion. So you know there is no right child. So you will insert new node in the position of right child and you will come out of the loop. So you're done with the insertion. You don't have to complete your level order procedure. So this is what we'll write in a pseudocode now, and then let us see what is the time and space complexity of this procedure. So this is the pseudocode. What you want to do? You want to do a level order traversal. Whenever you see a node without a left child, you will see insert new node there. Or if it doesn't have a right child, you will insert there. But the preference is for left child. If a node doesn't have both left and right children, then you will insert in left node, left child's position. So let us write the pseudocode. Insert. So this is a function for insertion. What do you want to insert? You want to insert a new node. Let us say you already have this node that you want to insert, new node. You are inserting this into a tree with this as its root. So you only need the root in order to identify a tree, because if you know the root, you know how to go to all other nodes, because you already learned many traversal techniques: pre-order, in-order, post-order, level order. So all these can be used. So here we are using level order traversal. What is the first thing that you need? You need an empty queue. So queue is an empty queue. Okay, this is empty queue. And the next thing is that you want to enqueue root into this queue. So you are enqueuing your root node. root node into the queue. Once you enqueue, what do you want to do? You can start the level order traversal procedure. So you will have a while loop. While this will run till the point your queue is empty. So while queue, what do you want to do? You will dequeue the first element from the queue. So node is equal to dequeue of queue. So from queue, you dequeued the first element. Once you dequeue, what will you do? You will check whether it has both left and right children. If it doesn't have any of those children, you will insert at that position and return back. So what do you want to do? You want to check if node pointing left, that is whether this node is having left child. If it is having, what should you do? You should enqueue that left child into the queue. So enqueue, if this is having it, then you should enqueue node pointing left into the queue. And if it is not, what is the else case? In case it is not, then this node pointing left is the position where you want to insert new node. So else your node pointing left, in this position you can put your new node that you want to insert. And in this case, if you already inserted the new node, you should return. Okay, in this case you should return there. And what is the other case? You want to check for right child. That is, if you have not returned already, then you should check for the right child. If node pointing right, that is, if there is a right child for this node, then what should you do? You should enqueue the right child, right? Node pointing right into the queue. This is what you want to do. And if the right child is not present, that is else case, what should you do? The node pointing right is the position for insertion. So how do you insert? You put new node into this position, new node, and then you can return. So whenever you are inserting, then you can return from there. You don't need to continue with the level order procedure. So if you completed this whole procedure, what does that mean? You will never complete this whole procedure. Why? You'll always find the position to insert before you complete this procedure. How can I say this? Just think about this. How can I say that you'll any day complete the insertion procedure, you'll find the position to insert and do the insertion before you complete this while loop? Why is it? Because in whichever tree, you take any tree, it will have at least n by 2 nodes as leaves. And whenever you have a leaf, you're sure that you can insert that. Okay. So even if you consider that all the nodes are full, that is if in this tree, all the nodes are completely full, still there will be n by 2 nodes, that is more than n by 2 nodes, which are leaf nodes. And whenever you have a leaf node, you can insert in both the left as well as right. So when it is a leaf, left is the priority, but I'm saying both the left and right positions are empty. You have to insert in left only. So it is never possible that you will totally come out of this while loop without finding a position to insert. So what is the time and space complexity of this algorithm? In case of time complexity, what can happen in worst case? In worst case, you may have to go through all the nodes of the tree till the last level where you find the leaves. Okay. In that case, there are almost n by 2 leaves, which means you have to already go through around n by 2 nodes, which means time taken for that is order of n. So n by 2 is order of n. What about the space complexity? Again, the same order of n, because it is possible that you may have order of n nodes in the queue. So space complexity that is consumed for the queue that you are using. Same as the case of level order traversal.